Okay, Guido, do you want to do the introduction now?
Yes. Hello, everybody. Welcome to the 14th LISA Symposium, second day. Today we have the plenary session number 3. This will be about the payload items within the MOSA. So we'll start with Daniele, who will talk about the GIS with the test mass in there. Ewan Fitzsimons will introduce the optical bench, and Jeff will talk about the telescope structure. And then Hubert will talk about the testing of the MOSA and parts, the subsystems together at a system level. And David will introduce the LISA International Networking Committee for Science as an add-on to this session. As we had got yesterday, if you have questions, please type them in the chat. Any questions which the audience submits is visible to everyone. Questions may be submitted anonymously. Private messages are visible to the host, so we'll see them. And if you wish to ask a question, maybe raise your hand or include a comment with your submitted question. Questions from a live stream on YouTube are also welcome. And the questions will be taken at the end of the presentation. I will repeat them, and then hopefully they can be answered. And that's it. So we can get started probably with Daniele Vetrugno from the University of Trento talking about the GRS with the test mass.
Okay. Can you hear me?
Okay. I can hear you.
Okay. I will try to share my presentation now. Okay. Can you see it in presentation mode?
Yeah.
Okay, perfect. So thanks, Guido, for the introduction. Thanks for the organizer for the kind invitation. Good afternoon and good morning to everyone, according to where you are. So I will talk about the LISA gravitational reference sensor that sits at the heart of the LISA sensitivity to the gravitational waves, together with the optical metrology system that should allow for our picometer accuracy in measuring the relative displacement between the test masses in faraway spacecraft. And you will hear about that in the next talks. And together also with the time delay interferometry that you heard about yesterday, this post-processing technique that allow to reduce the laser frequency noise that is otherwise overwhelming. The role of the gravity reference sensors is that of guarantee the quality of the free fall. So in such a way that you don't fool yourself by thinking that you are looking at the gravitational waves, and instead you are looking at a local force that is moving your reference test masses. And you can see other talk and poster from the UTN group, learn if you want to know more about the other aspect of the GRS. So the first point I want to make is that if you take this is a picture from the proposal, the characteristic train for LISA, and you break down it to the noise that compose this is done. This plot is done in the single link approximation, but I don't want to go through that. But the important thing is that below few milliars, you will recognize that LISA is dominated by the forced noise. That, as I told you, is what the GRS should guarantee, that we are below some requirement on that. And the problem is that forced noise, at least before LISA Pathfinder was launched, that we'll talk in a few slides, was poorly known. And this plot should, perhaps I can use the pointer. Yes, this plot should explain why. This is on the y-axis we have the amplitude spectral density of the differential acceleration, and on the x-axis the frequency, and the blue and the red curve are from previous upper limits, and the red and the black one is what we need for LISA in terms of acceleration noise. Now this is in acceleration. And as you can see, looking at the y-axis, these are order of magnitude. So this represented our ignorance at the time, both in amplitude and in frequency. That was enormous. And but the point is that the other point is that all this noise comes from is a local source of noise, so comes where the test mass is. And so you don't need the long arm interferometer. You don't need to put your test mass, your two test masses in too far away spacecraft together with the GRS and use the long link of 2.5 million kilometers to measure the force noise. And this is the base of the idea of LISA Pathfinder, that say, okay, let's shrink this distance to the famous 38 centimeter of LISA Pathfinder and put the two test mass in the same space, right? And in such way you can measure this acceleration of force noise. And if you want to know a little bit what was LISA Pathfinder, this is a movie that shows you that you freely floating test masses. In between there is an optical bench in which we build the interferometers, and these two objects here are the gravity reference sensor, also known as GRS. And I want to underline that these are LISA GRS in the sense that when we build LISA Pathfinder, we try to build a GRS, a gravity reference sensor, that was as much as possible equal to that one that will go in LISA. This won't be exactly the same because, of course, there will be changes in the spacecraft and so on. But we try to do this as much as possible equal in such a way to fully exploit the legacy of what we can get from LISA Pathfinder. And so let me explain a little bit how is built this gravity reference sensor. Of course, at the heart of this, there is the test mass, that is the reference mirror. That is a cube of gold platinum alloy, both for density of the material and from the weak coupling with magnetic field. Surrounding the test masses, there is an electrodowsing that acts both as a Faraday shield, so reducing any electrostatic, shielding any electrostatic field outside the electrodowsing, and also with its electrodes, and we see only a few of them, but there are on all the phases. It acts as a position sensor and the force actuation. So in such a way that, in addition to the optical bench and the interferometer, you can measure the position and the attitude on all degrees of freedom with these sensors, with the capacitive sensor, and you can apply force on the test mass if needed, and we will see that is needed to apply force and torques. Then here you see something that you should not be able to see. So some UV light that impinge on the test mass or on the electrodowsing that are both gold coated. And this is to exploit the fact that you can extract electrons by photoelectric emission by illuminating with UV light. And this is needed because, as I told you before, this is a freely floating test mass, so it does not any contact with the electrodowsing. And also you cannot, because otherwise the noise will be too much. And this means that you cannot attach even a wire to make the test mass to the ground, to the electrical ground. And so the only thing to make this test mass neutral, because it's continuous to charging up with positive charge from the impinging cosmic rays, you have to extract electron, for example, from the electrodowsing and put on the test masses. And then we have a titanium vacuum chamber that surrounds everything, and it is close and maintain the vacuum before the launch. And after the launch, a valve is open and there is a venting duct, like a pipe that goes to the other space, that allow to pump out to the other space the gas, the residual gas in the vacuum chamber and surround the test masses in such a way that you can reduce the pressure, and reducing the pressure, you can reduce the Brownian noise. That is one of the source of the noise or the acceleration noise for LISA Pathfinder. There are many other things in this. I won't go into detail, but another thing that I want to mention is the gravitational balancing. This I want to mention because it's important also for what we will do in LISA, even if with some differences. As soon as you have such a sensitive measurement system, and you have an apparatus and the test mass is fully floating, you will have a net force, a gravitational net force in some direction applied to the test mass. And you want to minimize this net force for a couple of reasons. One is that you want to control the test mass in such a way that it doesn't crash on the electrodynamic ending the experiment or the measurement of the observatory. And the other thing is that then you want to compensate it, and you will compensate with electrostatic actuation, but there is this simple message that for the actuation scheme that you have, as higher is the net force that you have to compensate, higher is the actuation noise that you will introduce. And this is the driving noise in LISA Pathfinder, for example. It will be also important, not the same, but it will be the torque noise that will be important for LISA, but the principle is the same. So what you do, you measure the position and the mass of everything, and you build your satellite in such a way to minimize this net force. And after that, after calculation on ground, you would put a balance mass to make the field, the gravity field on test mass zero, equal to zero. Of course, you will allow for some uncertainties. We build to have zero, but at the end we'll have some residual field, and our calculation allowed for hundreds of picometers per second square, and that you balance with electrostatic force, and the entity of the force that you have to balance will produce an actuation noise that is the big one. Okay, so this is the GRS in a nutshell. Now let's try to understand how we can what we get from LISA Pathfinder, and so how we can exploit this legacy for LISA. So when we launched LISA Pathfinder, we switched on the system, and the first thing that we discovered was that we were very good in prediction, because the blue curve here is what we thought. Our estimation with current best estimate of parameters, and there is this requirement for LISA Pathfinder and the requirement for LISA, and we were on top of that, of our estimation. At higher frequency, we were really better because the interferometer behaved wonderfully. After 1 year, we really improved, and we were very happy because we reached the LISA requirement. But it was not so easy, because if you take the raw data, what you get is the blue curve that then become the red one. And so we have to do several things has happened, and we have to do some correction. So first of all, time passed. And so the pressure reduced with time, and the Brownian noise reduced after 1 year to this level. Then also we recognized that we were very good at the end at balancing this force, the gravitational force that I told you just before. And this means that because this is smaller, you have a smaller actuation noise at the end. Then we have to do some correction. We have to correct for the spacecraft coupling that mix any motion of the spacecraft to the main axis of the measurement. And we also have to correct the low frequency for non-inertial force term. We recognize, we didn't expect at the beginning, that because the satellite, the optical bench is attached to the satellite, and this is the reference system from which we do the measurement, any angular velocity will couple through the distance of the two test masses, the famous 38 centimeter, to give an acceleration between them. And also any angular acceleration coupled through any misalignment between the optical axis and the axis joining the two center of mass of the two test masses to give you an acceleration contribution, an acceleration noise. And we can correct by that. And at the end, we get the blue curve, and so the yellow curve. However, as I told you, it was not so easy, not really, because we also see glitches. In particular, the glitches that ruin our measurement was the quasi-impulsive force that we saw. This is here an example. However, we were able to model it and to fit out to get again the yellow curve. And if you want to know everything about them, you have to look at the Lorenzo-Salvatore. Okay, so we get the yellow curve. We were very happy. But then you want to be able to understand fully this noise, because if you want to reproduce it in LISA and to understand that, you have to understand this. And so we made several experiments on board to measure the several noise components that form the noise budget of LISA Pathfinder. At the end, if you build up all, you get the black curve and you compare with the yellow one. And what you see is that below 1 milliards, there is an unexplained excess noise that reach 80% in power at lowest frequencies. Okay, so this is what we get in LISA, and then in LISA Pathfinder, and we want to fully exploit this in LISA. And the first thing to say is that, of course, LISA force noise was proved by LISA Pathfinder in the sense that we reached the requirement, but the unmodeled noise of which we don't know the source and the force glitches of which we don't know the source represents an important challenge for LISA. In the sense, for example, that you have to design a mission with requirements that are enough to minimize any possible source of this unmodeled noise and force glitches. And this is the first thing. The other thing is that LISA is a different satellite from LISA Pathfinder. We have a different spacecraft geometry. We will have a different control. For example, the Tesla will be free, drag-free along the sensitive axis, but controlling the degrees of freedom. We have moving parts like the MOSA. And so new noise appears and new strategies for the gravitational balancing, for example, has to be applied, as I will show in a moment. Also, some changes in the GRS will be needed. So we have a TRL9, as it's usually said. So an hardware proven in flight, we have to change a little bit. Like, for example, we have to change the venting duct because now it's passing through a moving MOSA and a moving spacecraft. We want to use LED instead of mercury lamp for the UV source because of reliability and durability. And so on. The other thing that I want to mention about the LISA force noise that in case you want to measure some force noise, as we did in LISA Pathfinder, in LISA, the measurement will be not between two Teslas in the same spacecraft in principle, but within two Teslas in two far away spacecraft. And this will require that you can do this only using TDI, okay? And this has some implication also simply for measuring the noise, not just for calibrating, but for measuring it. And I invite you to see the talk of Martina Muratore if you want to know more about that. So about the new balancing strategy, I want just to mention this because it's one of the main challenges that we have. We want to reduce, to balance the gravitational field, the DC gravitational field, to reduce the coupling of the Teslas to the spacecraft MOSA. And why we want to do this? In general, as I already told you, we will have, because of the apparatus surrounding the Teslas, is a body fixed force that acts on Teslas. This is due to the spacecraft and to the MOSA that are surrounding it. In LISA Pathfinder, when the spacecraft will jitter, we don't have the MOSA, but assuming the spacecraft, when the spacecraft was jittering, the body fixed force will move with the spacecraft, but also the axis joining the two Teslas is the sensitive axis will rotate together with that. And so the body fixed force will remain a DC force. But if now the jitter is rotating, I don't know if you can see the little animation, you will have that this DC force will have a noisy projection that will be mainly the spacecraft angular jitter multiplied by some parameter that is a sort of stiffness, if you want to see in a way, a coupling coefficient that translates this movement in a force along this axis. And this coefficient will depend on the body fixed force. So in general, when you have this type of effect, what you want to do is to design to have a zero value for the coupling coefficient. And there could be different strategies to do this. And important thing, this will be something that has to be decided together with Prime at the system level, but we devise a possible strategy that is this. We take the MOSA outside the spacecraft and you build a self-balanced MOSA in such a way that the force that the MOSA apply on the Teslas is zero or built to be zero. Then when you put the MOSA in the spacecraft, it will feel the field of the other MOSA and the spacecraft, and you will build the spacecraft in such a way to compensate its own gravity, the gravity of the spacecraft, and the gravity of the other MOSA. This is a possibility. Of course, as you can imagine, it will depend strongly on the design of the spacecraft and the MOSA. The other effect that answer, and it's very similar, but with some differences, is if the MOSA now jitters, and you know that the MOSA will jitter. Now we have at least two forces that enters. There are the residual force on the TESMAS due to the self-gravity of all the apparatus, and the commanded force that you have to apply on Y, for example, on Y TESMAS, on this degree of freedom, because you have to control the TESMAS. And because the strategy is that the TESMAS is free on the X-axis, but on the Y-axis, we have to control to keep both the TESMAS inside the spacecraft and inside the MOSA. Now, when you rotate the MOSA, in principle, both the TESMAS, both the body fixed force will rotate and will have a noisy projection on the sensitive axis. You can reduce this coupling coefficient, for example, doing the self-balanced MOSA, but also, for example, putting the TESMAS at the pivot in such a way that this term that they couple the spacecraft to the jitter of the MOSA 1 of this MOSA will be 0 if the TESMAS won't move in the field of the other MOSA, of the spacecraft and the other MOSA. That happens only if the TESMAS is at the pivot. Also, this effect will depend also on the distance of the pivot, so it will depend on the system design. Okay, so this is an example of one of the many acceleration noise that enters, and what I want to stress here is that some of these, like that one that I showed you in a moment, but also the thermal effect, for example, don't depend only on the GRS, but are system level issue. So this is some way fascinating because you have to know everything about, almost everything about the system to be able to take this under control. The other thing that I want to say is that this type of noise, like the balancing that coming from the unbalanced body fixed force noise, cannot be measured on ground. The only way is to have a measurement when LISA will fly. We can design, we can have a protocol, make a calculation, design for 0 and allow for uncertainties, but the only measurement will be in flight. And so we must design requirement and test and verification to keep under control any possible source of noise. And I don't know if I'm going too fast or not, but I have my last slide with my concluding remarks. So the success of LISA Pathfinder showed that we can build a GRS capable to reach LISA performance. The GRS will be very similar to what we have in LISA Pathfinder, with some modification, but very similar. However, in addition, LISA Pathfinder found this unexpected source of force noise, such as the quasi-impulse force on the TESMAS and the unmodeled excess noise at low frequency, which will require further investigation and careful design for LISA. As I told you, LISA Pathfinder was not fully representative of LISA, and so some new experimental and engineering challenge appeared, like those that I already explained. They seem to be under control, but as I told you, we require careful interplay between the spacecraft, the MOSA, and the GRS subsystem. And the final thing is something that I sort of mentioned in the presentation. Recent studies show that if you want to measure the acceleration noise at the relevant frequency in LISA, when this noise is important, this will be really compelling, giving only very rough upper limits. So it's important that instrumentalists should work hard to design a mission within the requirement, testing everything possible and verifying the rest. But I think it's also important that we start to build pipelines robust enough to live with the unmeasurable acceleration noise, in particular if you want to look for low signal to noise sources. And with that, I have done. I don't know Yeah.
Good. Thanks, Daniele. Yeah, that is a little fast. And you bring us back on schedule, and hopefully you can deliver the GRS on time.
Okay.
Too. Are there any questions in the audience? I don't see anything in the chat. Alistair, do I have the right screen here on the chat and Q&A?
Yes, Guido, there is not currently any questions, although someone has just asked one.
Yeah.
Yes, pouring in now.
Pouring in now. Okay, Daniele.
Yes.
This is from Daniele Nicolodi. Thanks for the nice talk. Are there any speculations regarding the origin of the impulse force and excess low frequency noise?
Yeah, there are speculation. We have something that we think is the most probable, likely reason for that, and it could be asymmetrical outgassing. So because we saw a sign of this in what we call I didn't talk about it, the so-called glitch fest, when we try to lower the temperature of the system, and when we reach, let's say, a few degrees Celsius, really a hell start to happen of glitches. And so we think that there is some mechanical stress that opens some little pockets of gas that then outburst and impact on the test masses. We don't have a smoking gun. There is now a paper, I think, already in the archive that will be published soon, and there is also talk from Lorenzo that will, I think, explain and try to show all the detail of that. We also think we will continue to study, and we also probably will try to do something, if possible, on lab with the torsion pendulum to see if we can see something similar. We can think about some experimental setup to do a measurement to check this. Yeah.
Okay, there's two more questions I have here. One is from Alexander Schulze. Could you elaborate why in the end cubes were chosen and not the circuit test masses, for example, Stanford proposed?
Yeah, I wasn't in the collaboration at the time, but I think at the end the scheme for actuating the test mass is cleanest, and you have a flat surface for as a mirror, and I think mainly the way in which you can control the test mass in the spacecraft, it's easier with such a test mass and then an electrodowsing. This is as far as I know. Probably people in the collaboration at the beginning, when this discussion were done and were very lively, I think discussion, can add in chat something.
Yeah, let's probably delay that discussion. It's a long one, an interesting one.
Yeah.
John Baptiste Bale asked, how well do we expect to know noise curves at low frequencies in terms of amplitude and spectral shape?
It depends what you mean. So what we can do is to try to build a system that will be below the requirement. The knowledge of the spectral shape and the amplitude with the number and the spectral shape, I think we cannot predict on ground. The only thing is to measure it in flight. But I think this seems to be challenging because one way to do it is using null channel, in which you suppress the gravitation. LISA is dominated by signal, right? Every time you won't switch, you cannot switch the signal. So
Daniele, yes? we are running slowly out of time. But
okay, sorry. So the point is that look at the presentation of Martina Muratore, and they can say that we can put just upper limits also in flight about this noise, the measurement of the noise.
Sorry, and Waldemar Martens has a question mostly about balancing in light of fuel consumption, gas depletion during the mission lifetime, and spacecraft motion too. Maybe you want to answer that in the chat window.
Okay.
Move on then to
I will do
the
it.
next presentation.
Okay, I will
Thanks.
stop sharing.
Okay, let's thank Daniele again.
Thank you.
And now we come to Ewan Fitzsimons talking about the optical bench. Hi, Ewan, take it over.
Hello. So let's see if this works. How does that?
Looks good to me.
Is that okay?
Looks good to me, yeah.
Okay, right. Thank you, Guido. So I'm going to talk for the next 25 minutes about the optical bench. Before I go on and show where we are with current design, though, I thought it might be useful just to give a very quick sort of history tour of optical bench designs and how things have changed over the years. And I'm going to start all the way back in 1999 when I was still in school. And in the LISA pre-phase A report, which was back when LISA was a cornerstone mission, there was this picture here. And this is one of the first recognizable pictures of something that you could identify now and say, that's definitely the LISA optical bench. It's very different. Many people will have seen this before, of course. It's got things like a test mass in the middle, and it's really just a drawing. As LISA progressed in the early 2000s and the industrial studies kicked in, this design was turned into a full CAD model. And you can see still we have this design where the GRS is actually mounted in the middle of the optical bench. So very, very different to the kind of thing that we have now. The first optical bench design that would be recognizable as something very, very akin to what we have just now comes from about 2006. And it comes out of the LISA mission formulation study that Astrium did. And you see something that looks akin to the kind of pictures we're basically still showing. The mission formulation study ran for several years, and there were multiple designs of optical bench that went through it. This particular one here might be quite recognizable because this is the one that appears in the LISA movie that AEI made that's on YouTube, and I think it's that many people have seen. But as we go forward, the designs get more and more detailed, and the detail builds up, and they also, you'll note, start to get bigger and increase in size. And as we move to 2009, and we're really starting to do a lot of work to understand what this thing looks like, it's getting bigger again, and then bigger again. And finally, we top out here in about 2010 with the optical bench being 580 millimeters in diameter. This was for old LISA, the 5 million kilometer LISA. But this is almost twice the size of the telescope. So this really wasn't going to work. Around this time was also when we had to descope for the NGO study. And it was during the NGO study where we had very, very strict constraints on how big the optical bench could actually be, that we ended up going for this dual-sided approach. So we split the functionality and said, right, let's just use the other side of the zero door, the other side of the base plate. And so we had this much more compact, almost half the size. Admittedly, this has a lot of functionality stripped out of it for the NGO design. As we move forward to the start of the current LISA studies in 2017, we've still got the dual-sided design, but the number of things on it has crept back up. So this was the 2017 design for the LISA phase 0 study. It had to be very conservative and include absolutely everything that we could ever possibly want to put in a LISA OB, and it became monstrous and huge. That gradually got whittled down until by 2021, a year ago, we had this design. And this was the design we had just heading into the mission formulation review a year ago. And we were all set with this. And then I got an email from Guido that some work they've been doing in Florida looking at how to test the telescope, which Jeff will no doubt talk about in the next talk. As part of that, they've uncovered an interesting coupling mechanism, which they thought might be relevant to the optical bench design as well and relevant to the telescope design. And did I think it was a real effect? Did we think it was a real effect? So what was this effect that was found? So here we have a view of the MOSA with an optical bench and a telescope. And we'd spent a very long time, years in fact, thinking of what happens when this moves. We talk about tilt-to-length coupling. We've been talking about it for ages. And this is all about what happens as the MOSA moves as a rigid body and how that produces cross-coupling. What we hadn't got into the details of yet was what happens if just the optical bench moves inside the MOSA. And what we have here, this is a cartoon showing this exact effect. And because we have an off-axis received beam, the beam received from the telescope is off-axis from the test mass probe, as the optical bench rotates, we get this extra path length here. So the green beam is just a drawing. The green beam will advance in phase, and we'll measure a phase in the science interferometer. However, at least in linear order, there's no extra path length in the test mass interferometer. So this is a noise term. This would be an extra noise, and it will just comes in as a function of this offset. So we'll get an extra path length, which is basically the offset times the angle. So if we want to keep the offset to a picometer, that means the angular stability of the OB, as it was a year ago, would have to be a picoradian per root hertz. And for the avoidance of doubt, that is not possible. So what's the remedy? Well, if we can't fix the angle, we just have to fix the offset. So we have to go and make the exchange with the telescope be along the same axis as the exchange with the test mass. And even that has a tolerance. We will have to do this to about 100 microns. But that is within the capabilities that we have when we build the OB. But it meant that the optical bench design we had a year ago had to be completely ripped up. Further, we'd always shown up when we started the dual-sided architecture, we'd always made a very, very deliberate choice that we put the detectors and the acquisition sensor on one side, and we kept all of the stable and interferometry paths to the other. The big benefit that this brought was that it meant we didn't require any particularly great stability or alignment between the A and the B side. Whereas now we are forced, because we can't have a beam coming from the same point on the same side, we're forced to go to the other side and do stable interferometry on that side as well in order to do the test mass. However, things have also moved on, and we have a solid zero-door bench, as I'll show later on, whereas when we first did this, we were thinking of composite benches and things like that. So it made sense to completely revisit what we do with the OB, how we do this architecture. And this has turned out to have quite a number of advantages, actually. So this is what we currently have. This is our new architecture. And we split it now. We have the local interferometry on one side. So you might consider this the LISA Pathfinder side. It's basically what it is. And then everything related to the TX-RX transponder, to the long arm, is on the other side. So I mentioned that this has had some advantages. If I show this plot here, this is all those designs that I showed you at the very beginning, plotted. So this basically is time on the x-axis, just designs moving forward, and the number of components in each of those designs on the y-axis. And I submit that the number of components is basically a metric telling you how complicated your design is. The more components, the longer it will take to build, the riskier it is that something goes wrong. The new design that we have using our new architecture sits here. So it's a massive reduction in the number of optical components required versus pretty much all the previous designs going all the way back to the original LISA study in 2006. And for comparison, LISA Pathfinder sits here. So the LISA optical bench is now only slightly more complicated in terms of the number of integration steps than the Pathfinder OB, which is a significant thing. So this is what the new design looks like. This is it without the beams turned on, but I'm going to run through it, step through the different paths to make it clear. So the first thing we need to do is get laser light from the laser through our fiber injector. So this collimates the light from the feed fiber from the laser. And then we have to send almost all of that towards the telescope. We go through an aperture stop on the optical bench. We then reflect from the point ahead mechanism that corrects for the point ahead to the far spacecraft. We have this beam alignment mechanism, which we use to compensate for the overall alignment of the system later down the line. And then we have a fold mirror that folds the beam up on axis into the telescope. As well as sending light into the telescope, we also have to receive light. So the first thing we do is we bring the RX light in, and we pick off a small sample of it and send it to the acquisition sensor. Here, this is just a footprint diagram. We don't know what this looks like internally because it's been done by ESA, and we don't have too much visibility of it yet. The majority of the RX light, though, goes to the science interferometer. So we pass again through another one of these beam alignment mechanisms to correct the alignment. And then we have mixed the green RX light with a small pickoff of the red TX light at the science interferometer. And then we have two imaging systems that image the internal pupil of the telescope onto the quadrant photoreceivers. The final thing that we do on this side is take off another small pickoff of the TX light and send it to the periscope optic. And this is now the only periscope optic. We used to have 8 of these to go between the A and B. Now we have 1, which is a big simplification in this design. So we come through to the B side, and then we have the B side periscope where the red TX light comes out. And we pick off half of that, and we send it via polarization multiplexing along another prism mirror up off this side towards the test mass. Again, perfectly on axis, mirroring the exchange to the telescope on the other side. We then interfere that with a sample of the local oscillator, which is derived over the backlink from the adjacent OB. And then we have 2 imaging systems which image the test mass surface onto the quadrant photoreceivers to get the signal. Finally, we also have a reference interferometer. So this is a sample of the TX and the local oscillator from the backlink, which is local to the bench. And here we have 2-beam compressors. We don't need imaging systems like we do in the other interferometers because there's no tilt to length to minimize, but we do need to compress the beam down to match the size of the quadrant photo receipt for the reference interferometer. Finally, we also need to, if we're going to derive light out of the backlink, we also need to inject light into the backlink. So we take a sample of the TX beam, it passes through an attenuator. This is a deliberate choice, which is used to suppress the noise that comes inside the backlink that will be spoken about by Leah Bishop giving a talk on this, I think tomorrow. And we inject that into the backlink that then passes to the other optical bench and forms the local oscillator beam on the adjacent side. So that's basically the new design in a nutshell. If you've followed that kind of brief tour through it, you'll have noted that for the most part, all of the optical paths are much shorter than they have been in any previous design. The number of fold mirrors required is very, very low. So it's a significant improvement for us, we think, on what's possible. And it's close to using the theoretical minimum number of optical components, which is actually required, which is a good thing. So looking just briefly at some of the elements that go into making up the optical bench. The first part I'm going to start with is the base plate, and we're making a very, very precision measurement, but that's only going to be as accurate as the ruler that makes it. And for LISA, a very, very significant part of our ruler is this base plate. Now, it might just seem like a dumb lump of glass, but it is crucial because its stability and its deformation and its alignment stability can affect everything, and it can ruin the measurement quite easily. So it's made from a material called zero-dur, which has a very, very low coefficient of thermal expansion. It's about 20 parts per billion. So it's 1,000 times more stable than metal. Unfortunately, we can't have a solid lump of this stuff because it's too heavy. So we have to have holes machined laterally all the way through. So these holes pass all the way clean through the base plate to the other side. And this removes somewhere between 40 and 50% of the mass. However, we still have 2 very, very nice surfaces. Via this process, we're left with 2 nice surfaces, and we're left with a zero-dur spacing between the A and the B side, which is crucial because we now require very good stability between the A and the B side in the new architecture. But this design of base plate should have absolutely no problem at all in delivering that for us. We're also very, very sensitive to the deformation of this. This is something we discovered in Pathfinder. We have on LISA, we're even more sensitive than we were in Pathfinder. And the maximum allowable surface gradient on the optical bench, so that's the gradient of any spot on the bench with respect to a best fit plane, as it were, is 3 microradians. So that's just over half an arc second. It's almost nothing. That's a challenge for polishing, although it is possible, but it's also a challenge for the mounting because deformation applied to the zero-dur can bend the base plate, and we can very, very quickly lose this. And if the gradient increases too much, the beams will just walk off where they're supposed to go, and we'll change the alignment, and it will add noise. So the optical bench is supported around its periphery by 3 titanium inserts. This photograph here shows a prototype of one of those inserts, and these incorporate special radio flexures which help decouple the impact of the alignment of the MOSA structure into the optical bench. And we have a dedicated poster on the optical bench baseplate by Zishan Ali. Another major part of the optical bench for us are these fiber couplers. These take the light from the fiber and turn it into a collimated beam. And we've put a lot of work over multiple years now into developing the Pathfinder design into something we can use for LISA. Why do you mean to do that? Well, the requirements for LISA are quite different. So we need a larger beam. It's almost double the size versus Pathfinder. We need significantly improved thermal pointing stability, a factor of 6. And we also need better wavefront error performance. And most significantly of all, we have to handle much, much higher power. So these were the fiber couplers in LISA Pathfinder. These are actually the flight ones that flew. The base design is that there's a silicon block with a fiber mounted into it. We then had a lens glued into a carrier, which was air spaced. So there was an airspace between the fiber tip and the lens. And then the whole thing was catalysis bonded together. And for Pathfinder, it worked brilliantly. So this is the basis of our LISA design, but we've evolved it quite a bit in order to meet these new requirements. So we still have the same fiber mounted in a silicon block, and we still have the same catalysis bonded mounting, but we have a new completely all silica-spaced catalysis bonded lens. So now the fiber to lens is completely enclosed in glass, and it's all affixed using hydroxide catalysis bonding. So it's much, much more stable, and it's much, much more resistant to contamination, and therefore with higher power handling. And later today, there's a dedicated talk all about this by Dave Robertson. Another important component of the OB are the imaging systems. So these are really important for minimizing tilt-to-length coupling, especially in the science interferometer, but also in the test mass interferometer. Previous work at these looked at lens-based imaging systems, and in many, many OB designs we've had before, including a lot of the ones I showed at the very beginning, we draw that in an optical layout diagram as 4 little lenses with a box around it, where the box represents some mounting. Very easy to put in an optical model. However, when you do the work and turn that into a design, you end up with something that looks like this. So this was a prototype for lens-based imaging. That's not necessarily a mechanical design that we would say would fly, but it is indicative of what is necessary in order to mount and allow the alignability of the lenses. So we've become increasingly concerned that there are 36 of these systems to fly. We've become increasingly concerned that this was going to take far too long to align and was going to be a bit of a pain. So over the last year, we've worked at completely redesigning these things from scratch. And what we've moved to is a new completely reflective system. So functionally, an imaging system made of lenses or mirrors does exactly the same thing. However, the big difference for us for a reflective system is that we can make the mirrors from 0 Dur. We can have a flat bottom polished on them, and that means we can catalysis bond them down. So it means that for us, these are going to be much faster to make. They're going to be much, much more stable because they're going to be all 0 Dur rather than lenses mounted in metal. We will get the same performance as we would expect from an imaging system in delivering tilt-to-length coupling suppression. And we have a dedicated poster on the new LISA imaging system designs by Bill Brzezowski. The final sort of element of OB technology I want to highlight are the beam dumps, which might sound a bit mundane, but they're pretty significant. In multiple places across the optical bench, we have to dump stray beams, which have potentially multiple milliwatts of power, even tens of milliwatts of power. And these must be dumped with high efficiency. So we're dumping samples of the TX light, for example, that are filtered through a polarizer, the rejected polarization. We need to get rid of it. The amount of power we put into the test mass is only 1 milliwatt, whereas we might have 10 to 20 milliwatts of rejected polarization power of the 2 watt beam. So there are stray beams that are much, much more powerful and intense than beams we actually make precision measurements with. So it's very important we have a way to dump these things. And the absolute minimum we need to achieve, this comes from the polarizing cleanup just before we launch into the telescope, is about 60 dB of suppression in order to not get a measurable noise. So in the layout diagram, we draw these things like this, but this actually is a design, and this is a prototype of one. It's based on angled plates of a special glass, which is, although a rather nice color in the visible, is blacker than black at 1064. And we use multiple reflections from very highly polished surfaces to attenuate the light away. We've also developed a system to measure how good these things really are. And this is a preliminary measurement. This is only a week or so old. The key measurement is the ratio between the green and or not the ratio, but the suppression from the blue to the green. And it's measuring at about 108 dB of suppression. So with a huge amount of margin compared to where we think we need to be. And there's a dedicated poster on this by Andrew Earle, talking about both the design of the beam dump and about the design of the measurement system we developed to do this. So the final thing I want to talk a little bit about is the OB integration. How are we actually going to do this? So clearly building 6 flight model LISA optical benches efficiently is a bit of a challenge, but this is something we've been working on for a very long time. Many people will probably have seen this video before. This is one of the final stages of actually building the Pathfinder optical bench. And it basically just highlights the fact that we really did do this manually by hand. We built the Pathfinder bench. You can see hands manipulating components and putting it down and trying to adjust the alignment. For LISA, this was never going to be the way forward. So what we have been developing for quite a while now is a robotically assisted method of doing this. We call it robotically assisted bonding of components. This is a picture from a few weeks ago of the actual OB integration facility at here at UKATC in Edinburgh. And this is us actually starting to install the first mock-up of the one that will really build the LISA flight OBs. The basis of it is a robot arm, which is a commercial robot arm, basically an offshoot of the car manufacturing industry. On the end of the robot arm, we have a hexapod that gives us 6 degrees of freedom precision control. Under the hexapod, there's a laser metrology head that I'll talk about a little bit more in a moment. And then finally, hanging under all that is the optical component that we want to attach. And what you have to imagine here is that this block of granite, which is the bed of the coordinate measuring machine we use, this is where the optical bench would sit. And we will use this system to bring the component down and drop it into place, completely replacing all of the craziness that is going on in the video on the left. So how does this actually work? This is the picture of the prototype in Glasgow, where most of the development for this happened. And then what we have here is a video looking in at this from the side, and then another video looking in at it from the top to give you a good idea of what's going on here. So this is the mirror in this case, which is mounted in the gripper. And we're holding it over this fused silica disc, which is basically a stand-in for the zero-dur base plate in this prototype test. So what we have here is from the metrology head, which is above the gripper and under the hexapod, we're sending a beam into the top of the component, and we're launching a laser beam down through it. Because there's an airspace between the component and the base plate, we'll get Fresnel reflection at both interfaces. So we'll get 2 laser beams coming back, one from the component surface and one from the base plate. And we can do interferometry between those in order to work out what the alignment of this is. We're actually modulating multiple frequencies into this laser, so we can do 2-color interferometry and get an absolute distance measurement. So we're measuring the absolute distance between the component and the base plate. And then we're also using differential wavefront sensing to get the tip and tilt. And we use these signals to feed back to the hexapod, and we hold the component, and you can actually see it here. It's being held about 200 microns over the zero-dur base plate. And it's aligned in tip and tilt to less than an arc second. So it's basically exactly where we want it to be when its catalysis bonded down, but held ever so slightly above the base plate. Separately, of course, on the OB, we also have a beam coming in, which is reflecting off this mirror. This beam will reflect from the mirror surface to our alignment target. This is the thing we call the CQP, calibrated quadrant photodiode pair. And this is pre-positioned in exactly the place that we want the laser beam to go. For example, it's positioned where we want where the test mass will be, or where the entrance to the telescope will be. We can then use the signals from that and feed back to the hexapod again, and we can align the component. So it's being held by the system pretty much exactly where we think it needs to be for the catalysis bonding process, but offset by 100 microns. And then we align the rotation and the position of the component to lock it onto the target. So at this point, we've aligned it in 5 degrees of freedom with laser metrology. The only degree of freedom we've not touched is the lateral across the component, which is the one for a flat mirror that we're completely insensitive to anyway. The next step, having got it aligned, we were holding it in the right place. We know we can get it aligned. It currently is aligned, but we need to get the bonding fluid in there. So we now need to lift the component back up by about 1 centimeter. So it's now been held up. The laser metrology is still working, at least on the bottom part. So we're holding it in tip and tilt in the right place. We're measuring the separation change as we go. We now need to bring in the bonding fluid, and this is done with a pipette, which will appear in just a moment. So the pipette comes in, it deposits the bonding fluid onto the zero-dur, and now we lower the component back down to about 100 microns off the base plate surface. So now the absolute metrology is still working. It's giving us about 100 micron offset. And at this point, when I unpause it again, you'll see, particularly in the video on the left, the system will start to step the component down in about 10 micron steps towards the bonding fluid. And at some point, it will touch the bonding fluid. And at that point, it kicks in and it increments it down until the bonding fluid has completely covered the surface. So I'll show that here. It's touched the bonding fluid, and that's it down with full coverage. So at this point, it's clamped in place by the system. Within about 10 minutes, the component will be set and won't be able to move, and we can release the gripper. So I spent longer explaining this than it actually took to do that. So when you add in all the prep time required and the setup time, we've transformed the process of bonding components from something that took hours and sometimes days on Pathfinder to something that takes between about 15 to 30 minutes, but much, much more importantly, is much, much more reliable and repeatable than it was in the process we used in Pathfinder. And I will stop there.
Yes, thanks, Ewan. That very interesting and encouraging talk. I'll see some questions coming in. So Natalia Kozakova is asking, are there any limitations from the precision with which hexapods could move?
No, we're limited actually by the target. Our CQP system is our alignment limit on the optical bench. So the difficulty is that we have to align the beam either to the test mass or to the telescope, for example, in absolute space. We don't have the telescope and we don't have the test mass, but they are defined in some mechanical coordinate system. And we have to align with, to 20 or 30 microns, a beam 2 or 3 millimeters across without having any other metric. So this is what this CQP system does, but it's limited to about 4 microns and about 15 microradians. The hexapod's about 10 times better than that. So we're not limited by the hexapod.
Okay, there's a very related question from Daniele Nicolodi. Awesome developments. That's true. Regarding the beam alignment with the target photodiode, doesn't this transfer the problem of placing the optics to placing the target?
Yeah, and I think basically that's the point. That's where we're actually limited. However, the system that we have for doing it is more than good enough to hit LISA requirements with margin.
And a person named Stefano Vitale is asking, do you need to control the loads of your holding screws during the process?
Do we need to control the load? Do you mean so we don't? Yeah. So the gripper design is quite special. It's undergone compared to what was shown in the picture there. What we currently have looks quite different. It's something that has gone through many, many iterations, and it does require care in the design that we don't damage the optics. It has to be able to hold them firmly, but not so firmly that it damages them.
Okay, and Timesh Mistry is asking about the crosstalk of the QPDs, onboard QPDs, to differential waveform sending with respect to the DWS error of 70 nanораds per square hertz. That's probably more a question for the photodetector folks.
What is the question?
Can you make a statement about the requirement on crosstalk in the onboard QPD to differential waveform sensing?
Crosstalk into the different DWS signal or crosstalk?
I
crosstalk
think
from what to what?
I think we take this offline.
I think this is an offline one, yeah.
Yeah. David Shoemaker is asking, you currently plan a single assembly station? If so, what are the limits for parallelization? Human resources?
Effectively, yes.
So it's a single station then?
We have one very large CMM in the lab, and we have one of these stations. I mean, we're also using the lab in Glasgow. So we'll be building subsystems for the OB and the Pathfinder integration lab in Glasgow, shipping them through to Edinburgh, which is 40 miles, so not far, and then integrating them onto the OB. So we're achieving a measure of parallelization by that. But the idea of having a complete duplicate OB integration facility, we're basically limited by people. And it's not just a money thing, it's people who know what to do is a major bottleneck.
Yeah, Daniel Penka has a question that's also one I kind of have. When you started counting the number of components and reduced to 30, that was 30 components you have to precision align and mount on the optical bench, right? It doesn't include really the imaging system and photodetectors, for example.
No, I mean mirrors and beam splitters. So it certainly doesn't include the photo receivers. They're separate. And I hadn't been including the imaging systems in that either. All the optical bench designs, apart from the latest one, they're not catalysis bonded elements either, and they're done separately as off-bench subsystems. So it's not quite a fair comparison to include them like that. It's just the mirrors and beam splitters.
And how are the bonds done of the imaging system? How is this? How are they? How is the imaging
We're
system
going to
bonded
use
to
exactly the same thing. The plan is to use the robot.
Okay, good. I think we stop here. We have now a break, and Joseph Martino's question is actually more for the telescope folks anyway. Okay, good. So have a break now, and I see you and see everybody in 15 minutes. Thanks, Ewan, again.
Thank you. Bye-bye.
Oops, it is 10:15. I want to continue now with the second part of this plenary session. After talking about the GRS system and the optical bench, we now go to the telescope, and Jeff Livas from Goddard Space Flight Center will tell us about the status of the telescope and what it's doing. Jeff, all yours.
Okay, thanks, Guido. Let me share the screen. Okay, and does that look correct?
That looks correct.
All right, good, thank you. Okay, so today I'm going to tell you about the LISA telescope manufacturing and testing plans. The work that I'm going to be summarizing here is the results of the efforts of a large, talented team, both at Goddard, the University of Florida, and Texas A&M. And we are working with a development partner, L3Harris Technologies in Rochester, New York. Before I begin, I want to mention some related talks in this symposium about subjects that are of interest. So later today, there's a series in instrumentation parallel session about tilt-to-length coupling that is useful background. And on Thursday, there's 2 talks of interest. Also, there's one on simulating micrometeoroid impacts. But more importantly, there's a dimensional stability verification talk by Ada Minska, who's going to tell you about the optical path length testing plans for this telescope at the University of Florida. There's also a pre-recorded talk that covers some of the details of the Monte Carlo analysis of the build process that I'm going to mention briefly in this talk. So here's an outline. I'm going to give a brief contract status overview, but then really try and focus on the requirements, how the design addresses those requirements, a little bit about how we check to be sure that we can build a pile of these for flight, and then some testing plans. Okay, so let me begin with the L3Harris contract. So just to remind you that the purpose of this contract is for technology development. The contract itself is for 3 similar units. So there's a structural thermal model for STM, and this is the correct structure. It's full size and all that, but the optics are ground glass. They're not polished or coated. This was basically to generate a practice unit and also get an early chance to do environmental tests to be sure that we understood how to make a structure out of glass. There's 2 complete telescope units to be delivered. Long term, we're expecting that we deliver one of the EDUs and maybe the STM to ESA. The other EDU will remain in the US for further testing. Here's a summary of the development timeline for this. So we started the contract basically at the start of the pandemic back in March of 2020. We're a little bit more than halfway through the contract right now. And the thing we're looking forward to in terms of milestones will be the December of this year delivery of the structural thermal model to the University of Florida to get started on the optical path length testing, and then a delivery of the first complete telescope unit to Goddard in May of next year for optical testing. If you heard the talk yesterday about the overview of where the mission stands, you'll have heard that that we're planning to try to go through adoption next year. And so that's a little bit earlier than we were planning. For the telescope, here's how we're planning to address that. So we need to show that we're at or around TRL 6, or at least have a credible plan to get there. We have all along made part of the contract environmental testing, so vibration, TVAC, that sort of thing, to be done at L3Harris. They will also be doing some level of optical testing to be sure that they meet some of the baseline specifications. We plan to do more detailed optical testing at Goddard and to do the optical path length testing with the University of Florida in parallel to the optical testing at Goddard. So for more detail on the optical path length testing details, again, there's this talk on Thursday by Ada Minska, and I will cover some of it briefly here. Now we're planning to use the STM instead of the EDU for the initial optical path length testing. So that's largely to get a jump in schedule. So we can get the unit, we hope, in December instead of in May. And it does require a little bit of different work to add optics to the STM because the STM doesn't come with optics. As I explained previously, we were trying to have a little bit less expensive and a little bit quicker route to a practice unit. So we're going to do an optical path length stability test to get going. We may need to follow that up with a test on an EDU later, depending on the results. So here's where we expect to be next spring. So we expect to have environmental testing results for both the SDM and the EDU, the first EDU from L3 Harris. And we hope to have preliminary results or at least a unit under test at the University of Florida for optical path length stability testing. So you can see from the schedule I outlined here that it's very tight timing, but we think we have a credible test plan. And that's what the review board will take a look at. Okay, so I'm going to move here into a review of at least the top level requirements and explain how the design addresses these. So let me begin with telescope functional description. You saw this picture earlier, but basically the telescope, the primary function is to deliver light efficiently on axis between spacecraft. So the measurement that we're making is a displacement measurement between pairs of test masses located in adjacent spacecraft. It means that we need to be able to support simultaneous transmit and receive of a laser beam. And optically, the telescope itself is an afocal beam expander. So it means it takes a collimated 300 millimeter diameter beam and compresses it to a 2.24 millimeter beam for the bench and vice versa on transmit. So that's a magnification of about 134. So once again, the application is precision length measurement, not image formation, taking pictures of stars or anything like that. So because we're in series with the displacement measurement, there's 2 copies of the telescope, on each arm. We need to keep the optical path length stable to about a picometer per root hertz. So at round numbers, the observatory noise budget is about 10 picometers per root hertz over that 2.5 million kilometer baseline. So we have an allocation of 1 each for the telescope. We also need to minimize backscattered light, the noise from that, and tilted length coupling, and I'll talk about that as we talk about the design of the telescope in a little more detail. So this table here just shows you some of the key optical specifications. I'm not going to talk about all of them, but the wavefront error at this wavelength, 1064 nanometers, lambda by 30 is 35 nanometers. We have a little bit more allocated to the telescope to accommodate the bipod interface with the MOSIS support structure, and I'll show you a picture of that later. The large pupil diameter or the transmit beam diameter is 300 millimeters, and that kind of is set by the link budget between spacecraft. The tilt length coupling, this is the as-built number, and I'll show you that we think we can achieve this with multiple units. And I already mentioned the optical path length stability. So when I talked about the functional, telescope functional design, I called out dimensional stability, coherent backscatter light, and tilt length coupling as 3 of the key challenges and design drivers. Here's how we're planning to address them. So for dimensional stability, we use a very low coefficient of thermal expansion material and good thermal stability. And so this means that from a material standpoint, we should be able to easily make that 1 picometer per root hertz optical stability number. And what's going to matter for the telescope as implemented will be things like the joints. So we have to do a good job on those. To minimize coherent backscatter light, we've adopted an unobstructed optical design and low scatter coatings. And of course, we're going to keep the structure itself dimensionally stable so that if there is scatter light, and there will be, that the phase is stable so it doesn't add too much noise. We're also working to minimize the tilt length coupling. So this coupling comes about from a number of different contributions. So we have a careful design to minimize the path length differences with field angle, and I'll show you specifically how we did that with the design in a couple of charts. We also have to do careful alignment of the measurement axes during integration with the optical bench, and Ewan just described some of that and what the tolerances are in the previous talk. Wavefront errors projected into the far field can also couple transmit angular jitter into an apparent length signal as well. So our strategy here is basically to keep the wavefront error as low as we can. If we have to specify specific Zernike terms, we can do that, but we prefer not to because it increases cost and risk for building the telescopes. And finally, post-processing can be used to correct residual errors. And I want to call your attention to a talk in the session later today that addresses just this topic. Okay, so the key telescope interfaces, there's optical, mechanical, and thermal interfaces. I won't talk too much about thermal interfaces, but I'm going to move on and review the optical design and show you how we address these. So here's a review of the design. So what I'm showing here is a side view of the MOSA, which consists of the telescope, the optical bench, and the GRS. I'm just showing the test mass here. And so optically, the telescope has 4 mirrors, and it takes a small pupil, which is also the stop from the optical bench, and maps it to the large pupil, which is actually centered on the center of mass of the test mass. So the mapping, this pupil mapping from the small pupil to the large pupil, is, if it's done properly, transmits only angle. That is, there's no beam walk. So that means if the, so there's actually a physical stop on the bench. If the angle of the light changes going into the telescope or out of the telescope, it only generates an angular change at the large pupil. And so the angular, so beam walk is normally understood as transverse motion of the beam. In this case, it also means that we minimize the tilt to length coupling, which is important. So the optical design of the telescope, you can see that it's off axis. So the secondary mirror is outside the main part of the beam. This helps minimize backscatter. So with a secondary in the main beam, there's always a part right on axis that is flat, no matter how curved the secondary mirror is. And that generates what's called a Narcissus reflection, which sends light directly back into the receiver. So keeping it, unobscured like this and off axis eliminates that particular effect. Another nice thing about moving the mirror off axis like this is it allows us to thermally baffle the telescope, which means that M2 does not see cold space, and that allows the entire structure of the telescope to naturally float up around room temperature, which means that we can exploit materials like zero door, which have very low coefficient of thermal expansions at or around room temperature. So that's another advantage. So the M3 and M4 mirror pair in this particular case, so the optical prescription is shown at the bottom there in that table. M4 is a flat, which helps with alignment, and M3 is actually a free form, and that is chosen to allow us to flatten the change in optical path length with field response of the telescope. So that's basically like the tilt to length coupling that's intrinsic to the telescope design itself. Here's a drawing showing the telescope mechanical design. And so we are making the entire telescope out of zero door, except for the bipods, which are titanium. And you can see that the bipods actually are what mounts the telescope to the MOSA support structure. So we don't have a lot of pictures to show at this point because L3 Harris is in the middle of assembling the STM at the moment. You can see at the upper right-hand corner, there's a picture showing the STM primary mirror assembly mounted on bipods and on the MSS. You can see, if you look carefully, that it's ground glass. It's not actually coated, but otherwise it's the same mass and the same structure. On the lower left-hand corner, you can see the secondary mirror. And again, that's just ground glass. It's not a polished optic, but that gives you some idea of what it looks like. The primary mirror for EDU1 has just been coated with a protected gold coating just this past week, and you can see a picture of that in the lower right-hand corner. So the overall structure, because it's made out of zero door, we make it in pieces basically for manufacturing, for ease of manufacturing. If you tried to hog it out of a single piece of glass, it's expensive. And if you make a mistake, you end up with a very expensive piece of junk. So making it in pieces and assembling it means it's a lot easier to polish and coat the mirrors. And it also means that if you make a mistake with during fabrication of one of the parts, you can either repair that part or make a new one and not have to throw out the entire telescope. But this puts a a premium on the joints, how you put the thing together. And we have a joint design as shown in the red box at the upper left there, where for all of the joints, we use matched pairs of epoxy pads on either side that are oriented perpendicular to the optical axis. So I show an example where the secondary mirror is being joined to the tower. So the tower is that boom piece at the bottom that is holding the secondary out in front of the primary mirror. And you can see that the epoxy pads are on either side of that. So the matched pairs of epoxy pads are intended so that if there's any change in the properties of the epoxy, for example, dimensional fluctuations as a result of thermal fluctuations, that you see the difference between those two pads, the difference in response. We also keep the pads oriented at perpendicular to the optical axis, so there's no direct optical path length change due to the joints. So all the rest of the joints are notionally like this. Just the M2 was just easiest to describe. Okay, now I want to describe a design update that we know we're going to have to do for flight, and Ewan mentioned this also earlier. At the University of Florida, folks uncovered the geometrical tilt-to-length coupling of relative angular motion between the bench and the telescope getting converted to path length. So this is a geometrical effect, and Ewan had a nice, actually a little video that described this. But here what I'm showing is basically that with an angular motion of the optical bench, you can see with the off-axis interface from the telescope that you basically swing that moment arm L_offset back and forth, and you generate a effective length change that's proportional to that tilt angle or the sine of the tilt angle. So that's first order in that angle. The interface to the test mass, by contrast, is right along the optical axis. And so your effect goes like the cosine of that angle. So it's second order, and it's much, much smaller for small angles. So the solution here is to make the telescope optical bench interface on axis. And here's what we did to do that. So we were able to find a design with 4 mirrors and moved basically the M4 mirror back up on axis on the back side of the primary mirror to generate an on-axis interface. Now, we did not change the optical design of the telescope itself or the basic optical design. It's still an unobstructed design. In fact, we were able to find a solution where M1 is the same design, same radius of curvature, and same properties as with the EDU. The M2, we had to make slightly stronger curvature, not very much. And M3 and M4, we had to put curvature on both of them to be able to make the small pupil end up in the same position for the optical bench. This solution is, I would still characterize as preliminary, and I'll tell you why in the next chart. But for the moment, this looks like a reasonable solution for flight, and we need to do some further optimization. So it's natural to ask at this point, okay, we know we need to change the design. What's the impact on the engineering development unit program? And the short answer is none. So it's just not practical at this stage. We're more than halfway through the program, and we've made all of the parts except for EDU 2 and 1, and that's actually nearly complete. So the new design that we have actually requires some further analysis, basically tolerance analysis, to make sure we can build it and align it. And so we just can't stop the program now if we want to hit the second bullet point there, where we're trying to demonstrate that we understand how to build a glass telescope structure that can meet environmental launch requirements and still maintain alignment. So without a pile of cash and a time machine, we can't really halt the EDU program and convert it over to the new design. So the plan was always to redesign for flight. Once the requirements for flight were known a little bit better, we expect there will be some other changes that need to be considered as part of the normal work for developing the mission. The main impact in our case was we had to rethink plans for testing the unit. So here's a little bit more on the kind of work that we need to do on this design still. So it turns out that one of the members of our optical team has developed a process for basically doing an exhaustive survey of the design space for 4 mirror freeform imagers. So he's going to generalize this process for 4 mirror freeform afocal telescopes. And so basically he follows a methodology shown in the block diagram at the left, where he starts with actually a first order design. He adds some constraints and also metrics, and then produces some outputs with a Monte Carlo kind of search algorithm that can cover the design space in as much detail as you like. So an example of the output is shown on the right-hand side, where you can see that there's a maximum spot size metric, which is basically related to the wavefront error. And then on the other axis is the speed of the optics. And so the mirror speed is so that's basically an F number. It's a proxy for alignment difficulty and also cost and risk. So we may not use exactly that metric, but the point is that we'll be able to search the solution space and pick a design that we think is optimum for being able to build a bunch of these units. So we're also going to consider looking at 6 mirror designs to see if they offer any advantage for assembly and alignment. The preliminary look at the 4 mirror design suggests that we'll be able to fabricate all the mirrors, but it may be a little bit tougher to align it. We're not sure until we do this work. So at this point, I'm going to shift and talk a little bit about some Monte Carlo analysis of the build process. I want to point out that there is a pre-recorded talk that covers this in a little bit more detail. And so the idea is that we took a look at the build process and included uncertainties both in alignment and assembly and the fabrication of parts. L3Harris did this as well. We used their same build process and included the fabrication errors, which they did not do. But here's an example of the kind of output that we get. So when you look at the RMS wavefront error, you can see that if you build 1,000 units, almost all of them are going to comply with the wavefront error spec. Same for tilt-to-length. So you can see that we easily meet the tilt-to-length spec for all of these units. And here's an example where we dug up a potential problem. And this is where it looks like we need to increase the tolerance on the radius of curvature of the secondary mirror. So if we use the tolerance that's on the drawings, you can see in the left-hand chart there that we're going to be out of spec on about 75% of the builds with respect to the diameter of the large pupil. That is the beam size. If we tighten up the tolerance, we can get to the point where we meet the spec on 100% of the builds. And it turns out that the optics that were delivered, actually fabricated, all of them met this tolerance. That is, they were within this tolerance of the nominal design value, maybe one of the most close. So the point is we use this analysis to help us understand how to build the telescopes and how to build a lot of them. I'm going to talk briefly now about testing plans. So at Goddard, what we plan to do is some optical testing. So I called out here bore sight, wavefront error testing, and pupil mapping. Things like the wavefront error testing, L3Harris is going to do this, but we're going to do it in a little bit more detail. So they will measure wavefront error basically down the center field, and we're going to do it as a function of field. I didn't put it on here, but we also plan to look at scatter light performance. Now, lab space, and in particular clean room space, is extremely tight at Goddard. This is due to the pandemic, so a lot of missions were not able to move along as fast as they had anticipated or planned. And so we've had to construct a clean tent in our lab. This is good for testing the EDU, but we'll have to do something a little bit fancier for flight. Here's a layout showing the wavefront error test. So it's basically a double pass test through the telescope. You can see on the right-hand side, we're using a 4D phase cam 6000. This is an interferometer at 1064 nanometers to inject light into the small beam side of the telescope. We have the telescope oriented on its side. This minimizes the deflection due to gravity of the telescope. And then we have an autocollimating flat on the very left-hand side to double pass the signal through the telescope. We're working with the University of Florida to do optical path length testing there. This will be a parallel effort. For more details, please again see this talk on Thursday. And I'm just going to outline briefly how the University of Florida plans to do this. This is kind of a standard method for making a precision stability measurement. Basically, you lock a laser, you make a cavity out of the telescope, and you lock a laser to that, and then you compare the frequency stability of that laser against the stability of another laser locked through a reference cavity that you've characterized previously. So again, for more details, please see the talk by Ada and Skan Thursday. Okay, so just to summarize, we've got a technology development effort of an all zero door telescope that's moving along. I think we have a credible plan to get close to demonstrating TRL6 by adoption. Looking ahead to flight, the key thing that we need to do here is determine the critical requirements for flight. And we're going to need to do some further design optimization once that those requirements are known. And I'll stop at this point. Thank you.
Thanks, Jeff, for the talk, for introduction, and also for mentioning Ada and University of Florida about 5 times. Hopefully she can give the talk tomorrow. She's COVID positive right now.
Oh, no. Okay, sorry to hear that.
Hopefully. Now I'm looking if there are any questions in the question and answer session. I should, before we actually take the actual one, we should go back to Joseph Martino's question about the TTL term, because that was more related to the telescopes. So Joseph Martino asked, I'm not sure I understand the new TTL term. Does that mean that internal angular stability of the telescope between primary and secondary, for instance, should be picorad per square root hertz?
Yeah, so it's a good question. And I think Ewan's got the answer there. It's a more complicated system. So the rigid body, the TTL that we're talking about, it's a geometrical coupling effect. For the telescope, it's more complicated. So we do expect that the telescope will essentially be a rigid body. We don't expect that the individual components will be moving around. We don't have a spec for picometer, a picoradian per root hertz angular motion. We wouldn't be able to verify that. It'd be very hard to do so. But we're planning to, but we don't have that kind of a spec anyway. The spec is on the overall path length stability through the telescope itself. And so that's what we're going to check. We won't be able to check that explicitly. So the answer is no, it doesn't really translate to that kind of a spec because the telescope is powered. It has, it's not just a geometrical effect.
Thanks. Daniele Nicolodi asked, why gold for the coating of the primary mirror instead of dielectric coatings?
Yeah, good question. So the simple answer is we want to control the emissivity, the thermal emissivity of the mirror, and gold is a simple way to do that.
Good, thanks. And Carlo Zanoni asked, do you plan any spacecraft plus telescope stop analysis?
Let's see, the telescope team probably not, no. So we do some stop analysis, but we don't really have a model of the spacecraft.
Yeah.
That's kind of outside our scope, yeah.
And Tug Stebbins is asking, what critical requirements for flight do you not know about yet? This is a question. Right.
So one example of a requirement that we would really like to know is the loads. So we would like to know the actual loads that the telescope experiences. So you know that the rocket, the launch vehicle itself, the Ariane 6.4, we don't really have loads for that, but we need to know what the loads that would propagate from a representative spacecraft through the launch adapter, through the spacecraft to the telescope looks like. And the reason that's important is it has to do with the interfaces. So the telescope itself is hanging off the MOSA support structure. And so the design of the bipods, for example, it's for the design of the bipods, it's important to know the loads in some detail. So we expect that the loads that we've used are envelope. That is, we took a worst case based on general guidance and best practices and that sort of thing from Goddard and also from ESA. And so knowing, having a bit better idea of what those loads are may allow us to do a little bit better design on the bipods and perhaps make the telescope a little bit smaller. That's one example.
Okay, and there was a question from, I believe, Linda, and Alice says I'm muting her right now, I hope. Linda?
Technology is wonderful. She may have raised her hand in error. We could take Sveta's question while we wait.
Yeah, okay. And Sveta is asking then if the new design, in the new design of M3 and M4, the mirrors are further separated than the former design. She does not quite understand why this reduces the tilt-to-length coupling. I think it best would be you go back to the design, to the drawing, I think, right? Because I think there's a misunderstanding.
Okay. So let's see. So I could go back to here. So basically the answer is that what we're trying to do is make this offset distance between where the beam is coming from the telescope to the center of the optical bench. We're trying to set that to 0. And so we need to do that. We need to set it to the same. We need to make the measurement axis of the telescope and that interface axis coincident with the axis going to the test mass to within about 100 microns. So in the configuration that I'm showing here, when you tilt the optical bench, you actually get a geometrical effect where that offset moment arm swings back and forth, and you get a path length change. I don't have a very good drawing here, but you get a path length change that's first order in that angle. Whereas with the test mass, you're actually swinging the that moment arm that's indicated there, the distance between the test mass and the optical bench. You're swinging it around, and you just get a cosine effect. In other words, it's second order in that angle. So the redesign, what it does is it actually moves that it makes the interface between the telescope and the optical bench look more like the one between the optical bench and the test mass. I hope that was clear.
Yeah. Okay, if not, we can probably take this offline.
Yep.
And Linda's hand was an accidental hand, so that's also done.
Okay.
She was just stretching.
Yeah.
Okay.
Thanks, Jeff, for the talk. And I think we want to move on to David at the University in Helsinki. David, are you ready? And you will be talking about the LISA Networking Committee for Science.
Guido, I think it's supposed to be Hubert.
Oh, sorry.
Yeah, I think it's supposed to be me, I guess.
Yeah, sorry. I was already getting ahead of myself. We need to test everything.
Yeah.
Yes, Hubert is actually talking about the testing of the LISA instrument at the system level and see how it all fits together. Sorry about this, Hubert. Take it over.
No problem. Okay, I'm sharing. Do you see my screen?
Yes, but not in presenter mode yet.
Yeah, not yet. Should arrive now.
Perfect.
Okay. Okay, well, so thank you, Guido. So I'm going to talk about testing the instruments, the LISA instrument at system level, meaning what can be tested and what will be tested once subsystems have been integrated and prior to launch. As you heard many times already, LISA is basically two kinds of techniques, let's say. We have one on the lower frequency range. We have the acceleration noise that was presented before. And this thing cannot really be tested on ground, and it was demonstrated in most parts by LISA Pathfinder. On the higher frequency range, that is above 3 millihertz, we expect to have a metrology noise that is of a level of a few picometers per hertz per instrument on LISA. And this has to be demonstrated on ground with specific test benches and to be as much as possible tested on the integrated system prior to launch. So this is what I'm going to talk about. That is, what are the different tests and how we are going to test LISA once it is integrated. So basically, well, you all know now that LISA payload is made of different subsystems. So we have what we call the MOSA, the movable subassembly, which is composed of the telescope, the optical bench, the gravitational reference sensor, everything connected by support structure, ultra-stable support structure. And next to this MOSA, we also have important system for the metrology, basically the phase meter, frequency distribution systems, and the laser source and stabilization unit. All these things will have to be integrated together to form the instrument that will be put on the spacecraft and used to make the measurements, to measure gravitational waves. In the integration process that is now planned for LISA, we have two levels of integration and verification. The first one, which is basically on the engineering models, that is quite early in the integration process, is what is named the interferometric detection system. It actually consists of the system, interferometric system core, basically that the optical bench, the phase meter, and the laser. That is what makes most of the metrology performance. This thing has to be demonstrated as early as possible with the integrated system so that the concept, metrology concept of LISA can be validated on a partly integrated system. Then once we have the ideas validated, we can move to the MOSA, which is a MOSA integration, which is a movable subassembly, which is basically what I've presented, what we have on the picture, with all the subsystem integrated together. This MOSA also needs to be validated and tuned for all the flight models, actually, and also the qualification models before launch. So this will have to be done on all the flight models, and because we are on ground, we cannot test everything. So we have to be careful on what can be tested, what cannot be tested on ground, and what do we validate and what cannot be validated on ground. So basically, the validation of the instrument performance for LISA is a complex task in itself, and it will require different dedicated optical benches that will have to be developed either for the IDS or for the MOSA testing. But also we need a detailed modeling of the disturbances and their coupling with the instrument performance. And both together will help us to infer what is the expected performance of LISA in flight. So if we go to the MOSA subsystem, that's in another view here, just to show what we have. You can recognize this on this picture. We have the optical bench in the middle. On the right, you have the GRS head. On the left, you have the telescope, everything linked together with the MOSA structure. And aside of it, you have the laser source with a stabilization system and the phase meter. This system has two main optical interfaces, optical interfaces, one with a distant spacecraft, which is so through the telescope, input and output, and one with the adjacent optical bench, so through the backlink, one way and the other, to exchange a laser between the two optical bench of the same satellite. If we reduce it to what is the IDS, so the interferometric detection system, we have that is basically, we remove the telescope, remove the test mass, and remove the structure between them, but we keep the core of the interferometric system. So the optical bench, the laser unit, and representative laser unit and representative phase meter. So we have, in that case, three optical interfaces. So one which is basically the interfaces to the telescopes, so a telescope interface, another optical interface with a test mass, and still the backlink interface. That will have, all these interfaces will have to be simulated in order to test the IDS system. So what do we want to test at IDS level? Why do we want to make some tests at IDS level? Well, the main goal is to validate the metrology concept of LISA on an integrated system. And basically, is the partially integrated instrument behaving as predicted? And we also believe that at the IDS level is the only integration level where we can directly test high stability, make high stability measurements on the different interferometers separately, with at least partially integrated systems, that is with the optical bench, a laser, phase meter, etc. This has to be done actually as soon as possible so that we can validate the concept and go for the flight models. So this will be done, this test on the IDS will be done as the engineering model or equivalent models. So what kind of tests can we do at IDS level? Well, we can all do everything that is combining the performance of the optical bench with the phase meter and the laser. So that means, for example, low power transponder lock, that is how to lock the takes beam, the transmitted beam on the received beam with the low power, to test beam power stabilization with the full chain, to verify the amount of tilt to lengths that we can get that we will get on the optical bench, and to check that the composition concept using the BAM is working as predicted. We can also test some field of view and corresponding DWS response, that is measurement of the relative beam pointing between RX and takes, and of course the whole phase acquisition chain. That's for the functional and calibration test. And of course IDS will be extremely important for performance test, that is basically testing separately the optical stability of the different interferometers, measuring the tilt length coupling, already actually talked about it, and also, for example, test the performance of the interferometer for tilted, equivalently tilted test mass. So how are we going to do that? Well, you saw the sketch of the IDS just before, but then we will have to design and build dedicated ground support equipment, mostly optical ground support equipment, to interface the IDS with the rest of the world and to simulate the optical interfaces. This is a sketch of what we plan now. So you still recognize in the middle the optical bench, and with the laser and the phase meter. On one side, so to simulate the interface with the telescope, we will have what we name right now a beam simulator, which is basically dedicated to simulate the characteristics of the beam coming from the telescope. So for example, about 600 picowatt flat top incoming to the optical bench, about 1 watt, receiving about 1 watt of laser from the optical bench. That will also allow to modulate the direction of the RX beam with respect to a reference beam, so that we can measure the tilt to length coupling, which is a major source of this potential disturbance on LISA. We also have to simulate the backlink, that is to receive a few microwatts from a fiber from the optical bench and send back another laser phase locked on this one. And of course, we will have a lot of phase measurements between the different lasers, so that we can measure the phase stability of the system. This bench will have to be fed by lasers. So we have a master laser that is frequently stabilized on iodine, and on which different auxiliary lasers will be locked. So reference laser, a laser representing the RX beam, and another one representing the backlink beam, and with a representative frequency offset for LISA. On the other side of the IDS, you have the test mass. So here replaced by the test mass simulator, which is functionally equivalent to basically a gold-coated mirror with very high path length stability, and that can be actuated in tip, tilt, and piston, and which will be also representative as much as possible of the optical interface. That is, for example, including a representative window between the test mass simulator and the optical bench. And of course, since we are on ground, we have to be very careful of the environmental disturbances. Oh, sorry, I forgot. We also need to have a very stable structure, because in that case, we want to measure separately the performance of the long-arm interferometer and the test mass interferometer. So we need to be very stable between the different pieces of the IDS. And so, yes, since we are on ground, we need to basically shield the system from environmental disturbances. So in the present concept, we have two vacuum chambers, one for the critical items, which has to be very stable in terms of temperature, so which should be held at a few microkeV hertz. And we have another vacuum tank for the electronics, which is supposed to be more noisy and which may have to be similarly stabilized at some temperature. Yes, and it also will serve as a shield for seismic noise, for example, and vibrations from the different from the surroundings. So this is another sketch of how it could look like. So you see a preliminary design of the infrastructure, where you see the three elements of the IDS testing. So the beam simulators, the optical bench, and the test mass simulator stacked on top of each other. And this thing is about 60 centimeters diameter, about 1 meter high, and will be put in a vacuum chamber, as you see here, with thermal shields and isolated from the external disturbances. And on the side, you have the second vacuum chamber with the electronics. So actually, the IDS, as I said, is relatively early in the integration process, and we expect the IDS system to be tested by 2026. So this basically is a short-term project. So that was for the IDS. And once we have validated the IDS, we go for integration of the instrument, that is of the MOSA in our case. So basically, MOSA will be integrated by the industry, prime by the industry, but the industry will have, under the recommendation and advices of the consortium, we have to test different key elements and different key performance on the MOSA, on the system. So basically, we want to test the qualification and flight models of the MOSA. And one key difference is, for example, between qualification and the flight models is the fact that the test mass on the flight model is grabbed and probably is present and grabbed in a direction that probably cannot allow to have any useful interferometric measurement of the test mass interferometer. So it prevents a direct measurement of the performance of the test mass interferometer on the flight models. But actually, it can be done on the qualification model with a fake test mass that is basically a test mass simulator on the qualification model. Anyway, to test qualification and flight models, there will be specific GSCs that will be developed and delivered by the consortium. So what do we want to test at MOSA level? Well, we want to check that the system is behaving correctly, that is, it is in good health, and also that the metrological functionalities after integration have been are still similar and still okay. We also want to check the interferometric performance against the prediction we can do using the performance model. So the prediction from on-ground disturbances, that is, we are going to use the knowledge of the ground disturbances to predict what we should measure on MOSA on ground and check against what we have. That will help us to, that will give us indications that, okay, the system is correct and behaving as expected. We also are going to measure and reduce the tilt-to-X couplings that are crucial for LISA. There will be some misalignment during the integration, and this will have to be compensated using the beam alignment mechanisms prior to launch. So on all flight models, we will have to measure and reduce the tilt-to-X couplings. And also another point that is important for LISA is to ensure that we don't have too much stray light in the system. So we will have to measure and identify any contributor to the stray light and to see if it is conform to the requirements. So, yep, why it does not want to change. Okay, computer is a bit blocked now. Sorry, I don't know what's going on.
I didn't take over control here.
You took over control, or
No, I didn't. I didn't.
Sorry, it's my. Yeah, okay, I'm resetting and see if I'm moving right. Okay, this time. Yeah, okay. Seems to be. Sorry for that. Okay, so let's see a few examples. So one of the major measurements that we want to do at MOSA level is the measurement and reduction of the tilt-to-length coefficient. Tilt-to-length coefficient is a coupling between an angle, a depointing of the incoming or emitted beam with respect to the nominal direction, and it's this coupling of this angle with the phase, that measured phase. So there is a TTL coefficient on the received beam, what we call TTL RX, and a TTL coefficient on the emitted beam, what we named TTL takes. TTL RX can be directly measured using a specific GSC ground support equipment, that what we named far field optical ground support equipment, because we need a large beam, and it's simulating the field coming from the long distance. So this will be, that's what is sketched here on this drawing. That is an apparatus in front of the optical bench and telescope that will be used to tilt the incoming wavefront in a controlled manner and to see if we have a coupling with the measured phase. But on the takes direction, well, it's not possible to measure it directly. So basically, the idea will be to characterize the wavefront error and the centering of the beam that is emitted by the MOSA, and to deduce from simulation what is the TTL, and from that correct it using the bands. So this is one important test. Another important test will be to check to some levels the internal stability of, the stability of the interferometer once it has been integrated into the MOSA, and to see if we can, if we have the required stability. So basically, the idea will be to test the optical bench internal stability against the stability of an external optical bench, so a trustable bench, and basically we are going to measure the joint stability between these two optical benches. And this system relies on the fact that the optical path length between the MOSA and the external bench is reciprocal. That is, we are measuring basically the optical path length in one direction and the optical path length in the other direction, and they should compensate to the level of stability of the optical bench itself, both on MOSA and on the external system, external GSC. So this is another test. So you see it's basically sharing the same configuration as the FOXY, as the TTL measurements. So that's another test that is going to be conducted at MOSA level. And another test, so that is important at MOSA level, and that basically is using a completely different setup, is basically to measure the amount of stray light that is produced within the interferometric system. So what is this? For example, the ghost images, the diffuse light, etc. That can couple, not cope, the thread that can couple into the interferometers, and that will induce phase, and that might induce phase fluctuation, phase noise, if this stray light is generated by unstable interfaces, that is, unstable surfaces with unstable optical path lengths. So the stray light or GSC, so what we named SLOGZ, is going to be basically deep modulating with a linear frequency linear deep frequency modulation, of a laser that will be sent into the system. We are going to record the current coherent signals on the different photodiodes. And because of the linear shift of the frequency, the disturbances due to stray light will appear as a periodic signal whose frequency actually depends on the distance of the contributor to the splitter, to the interferometric splitter. So basically doing that and afterwards having a Fourier transform will give the amplitude and the localization of the interferometric, of the stray light source. So that is going to be tested on ground. And so that's basically the different main measurements we plan to do on the MOSA. And just to give you an overview of what is the status of these different projects and test benches, we have basically a joint effort made in France to design and to build this kind of GSEs. So I'll show you here some of the different institutes collaborating, and we have basically different projects going in parallel. So we have started developing traceable prototypes, traceable benches, first on using metallic interferometer just to qualify the end-to-end measurements and to see that everything is going well before going to a zero-J interferometer that is going to be delivered in September. So we will have a test campaign from September to January, and we'll see what kind of stability we can achieve on ground with a representative kind of optical benches. And after that, well, and actually in parallel, we are designing the IDS test benches with preliminary design that should be done by the end of this year, beginning of next year. And actually right now, we are also identifying the infrastructures that are required and conducting mechanical and thermomechanical studies specifically for this IDS test campaign. And on a longer term, we have the MOSA test benches that are basically sought already with some prototyping for critical techniques for the SLOC-Z and the FOC-Z. And also the testing plan is being consolidated with the prime candidates in order to include that test into their integration process of the MOSA. Okay, so that was an overview of the tests that are planned at system level, so IDS and MOSA. And yeah, I think I will stop here. Thank you.
Thank you, Hubert, and apologies again for missing you.
No problem.
Hopefully that seen it as a Freudian slip or something like this, because scary plans. Let's see what questions we have here. Anywhere? Is there anything on the chat? Okay, I don't see any direct questions. I think the complexity scared the audience a little bit. Let me ask back about the picometer measurements that you mentioned. How realistic is this, and how much are these actually really needed, right? I mean, the optical bench as a standalone item, measuring the stability of the components at the picometer level does not require a telescope or really a test mass, right? You need to just put some mirrors at the back end and return this. And the TTL and TTL coefficient measurements doesn't need to require picometer stability either, right? Because you're really measuring transfer functions.
Well, we need I mean, for TTL, we need to be stable enough, not at the picometer level, but we need to be stable enough so that we can isolate the signal from the TTL from the noise. I mean, we have to get above, we want to measure something like 10 micrometer per rad, which is not so high. So we need to be able to get out of the noise. Anyway, we also want to measure the performance. We want to basically, I mean, we cannot just put a mirror actually as a instead of as the output of the optical bench, of course, because we won't have heterodynamic interferometry anymore, and we are not aligned. So we need basically to record the signal out of the optical bench and to send it back. We also need to achieve some kind of realistic contrast. So we have 1 watt out of the optical bench. We need to feed it with something like 600 picowatt. So that has to be done to check that we are not, that it's working with that level of power. Right now, we expect to have an external bench that is basically at the same level of stability as the optical bench of LISA. So the joint performance should be at the level of about 20 picometer per root hertz, but not at the millihertz. We don't expect to be extremely stable at the millihertz level because of the perturbation of the environment. So we might achieve that at a higher frequency. We think that it's still useful to check that we can check some kind of picometer per root hertz stability, even if it's not at the lowest frequency achievable by LISA, but at least to see that all the noise that we have predicted are below the levels that is required for LISA.
Okay.
So
yeah. So the I saw on your last slide, not this one, the one before, that you have a testing campaign coming up in the fall.
Yeah.
And then you want to be done with the final testing in 2026, I believe, when I saw this correctly. Okay, this is not going into adoption in reality, right? I mean, the test plans will be reviewed, but it's not going to go into.
No, we by adoption we need to have a design. We need to have a preliminary design of everything.
Okay, good. I still don't see any questions coming up, so let me thank you again. And then we can move on, and I'm sure we have to talk about the testing campaign quite a bit in the future. It's really a great challenge ahead of us.
Agreed.
Thanks. Yes, thanks. Okay, David, you want to talk today? So actually we are ending more or less the plenary session discussing the payload items, but David wanted to talk about an internal networking committee for science, introduces it here. David is in Helsinki, and I think, David, it's all yours.
Thanks, Guido. Thanks for the invitation to speak. Hopefully my video is visible to everyone. And yes, both exciting, but also a bit terrifying not to be talking about science. So let's, but I hope, I stand between us and the break, so I'll try to keep this fun and short. So what is LINX? So LINX is this kind of internal organization of the LISA Science Group. And one of the motivations for that is if you look at the number of members of the LISA Science Group, it's 1,000. And as of today, if you look it up on the directory, it's 1,249. So it's the vast majority of the consortium are actually within the LISA Science Group. And that itself is a colossal number of people, which are difficult to kind of keep in line and assign to work package teams, as well as kind of help them find their place in working groups. It's a highly non-trivial kind of marshalling exercise. And lots of people tell us that they're not sure how to contribute to the consortium within the LSG, and other people aren't aware of how to get onto work package teams or even what working groups are available to them and how to join them. In addition, the consortium has several kind of narrow points of failure or kind of bottlenecks, which we want to kind of try to smooth out and improve the communications so they run more smoothly. So this is definitely an LSG specific thing, but we hope that what we're doing will benefit other parts of the consortium as well, just kind of as a kind of trickle down side benefit from that. So when you sign up to the consortium kind of as a new external group, you're asked to your membership is set, your application is sent to the MMT, and one of the things they're looking for is, especially if you're a full member, then you're committing FTE to one or more of the work packages. So you're actually contributing to the goals of the mission. And one of the problems is that yes, people write this down, but then they don't actually know how to get involved in those work packages. They're actually just putting things down, and then they're not contributing in a meaningful way to the actual science of the mission. And we want to kind of make it easier for people to find their feet in these work package teams, as well as the working groups more generally. So that was the kind of motivation behind LINX, and it was set up by Elena Maria Rossi in particular, and some other people from LSG, and I, along with some other people, volunteered and got picked up along the way. We have an email address which you can email us at, so it's lsg-links@lisamission.org. We originally planned this exercise to last a year, but we found more and more things we want to do. So we're not necessarily going to give up after a year. And the other members, in addition to Elena, are Gianluca Calcagni, Anna Heffernan, Shane Larson, Jess McIver, Gijs Neelemans, Marta Bolinteri, and myself. And when people are not outside and at the beach, then we meet every 2 weeks. And our goals, as I've kind of introduced over the first couple of slides, as I've motivated this, are to improve communication and information flow, as well as the allocation of resources and people within the LSG, as well as hopefully kind of as a side benefit, improving the communication within the consortium more generally. So that is kind of what we're aiming at. And then kind of trying to increase the awareness of the different work packages to which people can contribute, and get them to kind of, as we especially head towards adoption, making sure that these work packages are properly staffed with people who know how to deliver the science we need to do as set out in the Edinburgh document. In addition, there's a lot of things for which we need people to do to understand the science involved, one of which is, for example, the simulator pipeline. And we want to kind of facilitate and encourage people to actually, for example, host training sessions for that. So for example, there was a very successful LISA simulation workshop run by Jean-Baptiste a few weeks ago. And we're strongly encouraging that sort of thing to happen again, and not only happen for the simulator pipeline, but for other aspects of kind of the deliverables for LISAs, that as many people as possible within the consortium have an overview of what's going on there. We have a wiki page within the IN2P3 wiki, and on that, firstly, we have a list of the people and what we want to do. But also, this might be useful for everyone, not just LSG members. We've tried to collate every possible, there's multiple different services and platforms used by the consortium, ranging from Atrium to multiple different Slacks, to mailing lists, to the directory. And we have an internal spreadsheet which we keep up to date within Links, and we every so often we dump it to this wiki page, which tells you how to log into these things, any tricks you might need to know, for example, how to actually log into the GitLab on IN2P3 if you need to access that, and kind of what errors you'll see if it's not working and how to get around them. So you can also check out this wiki page if you are not, to kind of get an overview of the different ways to access information within the consortium. And we're also looking we're also exploring options to kind of help consolidate these things and make it easier to find information across these different platforms. One platform in particular, which even now I think some people within the consortium are unable to access, is the directory. So the directory is important for managing your membership of your external group, as well as your internal groups, and also for accepting the privacy policy and the code of conduct with the consortium, which is something which everyone has to do. And you may have received emails about that, and you should definitely go in and do it if you haven't already. And if you can't remember what email address you signed up with, if you can't remember your password, you can recover your password. And if you can't even remember your email address, then the thing to do is email the membership management team, whose email address is mmt@lisamission.org, to get access there. So that's one of the key issues that we want to address, is kind of people gaining access to resources like the directory, so they can find themselves and get on the right lists and groups as well. We also are involved with providing input to the LISA Science Group newsletter, which is hopefully going to be a quarterly exercise going forwards. And the way that works is that it has kind of a summary of what's going on, as well as information and news from the working groups within the LSG, as well as the work package teams. And again, not all work package teams are necessarily active yet, but as they do, this will be the single point of contact to find them. And if you want to look at the back issues, if you don't get the LSG emails or something, you can find them on the wiki at the link at the top here as well. So you can definitely, that's accessible via the LSG wiki page there as well. On the public facing side, although it is mostly for the benefit of, well, partially for the benefit of LSG members, there's a public FAQ now in the consortium user guide, where we try to address some of the issues that come up most often. For example, when to contact the MMT, what to contact them with, who can become a member, what the duties of members are. Of course, some of these things are still in flux, as, for example, the nature of associate and full membership gets kind of become more concrete over the coming years. But we'll try to keep this FAQ up to date. And if there's something you can't find on there, then do let us know, or there's some calls to action and ways to get to help us with the FAQ on there. But we're very happy to maintain it or research answers to questions which come up regularly for this. But this is a public-facing FAQ, so this is accessible to everyone via the consortium user guide. Going forwards, we have a few activities. So we want to reorganize the internal wiki pages to be a bit more useful to everyone. There's a lot of kind of very blank and kind of a lot of the information in the wiki is in a couple of very dense places, and much of the wiki is very sparse. And so one of the things we're kind of going to do is improve the usefulness of the wiki for accessing information relevant to the LSG. We're also looking at finding all the different Slacks. For example, there's a consortium Slack, as well as the cosmology working group, for example, as a Slack. And all these, so there's information about these kind of different Slack groups spread across various different places, and we're going to try and consolidate that. And as I mentioned, we're going to try to kind of support and encourage further training training sessions, perhaps in connection with symposia and large consortium meetings. So, for example, on the simulator pipeline and other activities. And we also want to make it easier for people to we want to lower the threshold to people becoming involved in work packages and things like that. So this is what we're aiming for. So to conclude, we want you to, if you're a member of the LISA Science Group, or if you're even just curious, please feel free to check out the LSG newsletter to find out what the different work package teams and working groups have been up to. If you want to get involved in something, please don't be shy. Please do contact the work package team chairs directly when they've been appointed. And if you're not sure what to do, or you have an idea which I've not mentioned, or you have feedback on my presentation, please contact the links email address, lsg-links@lismission.org. And with that, I'll stop. Thank you.
Thank you for that summary of the links activities and also for the activities themselves there. Are there any questions? Jean-Baptiste has one, I think. I put it up here. Thanks for this. That will be super useful. Do you have any plans to include this in the LISA Consortium user guide? It was meant to be the entry point for consortium members.
So Jean-Baptiste, you're referring to I think you're referring to FAQ, and that's already live there. The version that's on there has a couple of issues with the markdown rendering, but we're making some merge requests, so that should be on up to date soon. And yeah, so the answer is yes. The FAQ will be on the user guide if that's what you're referring to. So thank you for the question.
Yep, thanks. Yeah, that answered this question. Any other questions from the audience? I don't see any. In that case, I think I want to thank all the speakers again for that lively session, and also all the people who asked questions for the lively discussions. And I think we have a longer break now, and we see you then at, when do we continue? Today at 2000.
2.5 hours, I believe.
2.5 hours from now in the parallel sessions.
Yes.
Thanks, everybody.
Thank you, Guido. Thank